All right, so today we're going to be finishing up pretty much chapter 5, 5.2, the rest of 5.2, 5.3, dabble a little bit of 5.4. What I don't get for 5.4, I will take 30 minutes to 15 minutes to do that, and then we're going to have the homework set is now due on the 29th when we get back from Thanksgiving. So here's the deal. Let's take a look at this guy here. So always start a good problem session lecture day with a question. Find the characteristic equation of matrix A, where A is equal to 2, 10, 3, 9, 0, 2, negative 2, 5, 0, 0, negative 4, 1, 0, 0, 0, 7. And then find the eigenvalues, okay? So, I just wanted to show you guys this, but this is actually a trivial problem. But I'm going to do it the way that we do all problems, and that is to find the characteristic equation, I have a formula. It is the determinant of A minus lambda I. That is the formula for the characteristic equation when you set it equal to 0. So, from this, we're going to take the determinant of matrix A, which is 2, 10, 3, 9, 0, 2, negative 2, 5, 0, 0, negative 4, 1, 0, 0, 0, 7. And I'm going to subtract off lambda times the identity. Now notice this is square, 4 by 4. So lambda times the identity would be lambda on the diagonals. Is lambda 0, 0, 0, 0, lambda 0, 0, 0, 0, lambda 0, and 0, 0, 0, lambda. It just puts lambdas on the diagonal when you do lambda times the identity. So, and we're going to take the determinant of it and set it equal to 0. So this will imply that the determinant of 2 minus lambda, 10 minus 0 is 10, 3 minus 0 is 3, 9 minus 0 is 9, 0 minus 0, well, that's pretty much 0, 2 minus lambda, okay, negative 2 minus 0, which is negative 2, 5 minus 0, which is 5, 0 minus 0 is 0, 0 minus 0 is 0, negative 4 minus lambda is pretty much negative 4 minus lambda, 1 minus 0 is 1, and then 0, 0, 0, and then 7 minus lambda. So that's what it boils down to. And you want to take the determinant of this guy, okay? How do you take a determinant of a 4 by 4 matrix? Well, we can do expansion by minors, but you also should notice that this thing is actually upper triangular. That was a real hint there, but I want to show you basically the way you should do it. I'm going to expand by the first column, reminding you about determinants from chapter 3 there, okay? And chapter 4. All right, so here we go. This would be equal to 2 minus lambda times the minor matrix. When you knock that row and column off, you end up getting this, 10, 3, 9, excuse me, row and column off. It gives you 2 minus lambda. 2 minus lambda there, negative 2, 5, and then 0, 0, negative 2, negative 4 minus lambda, 0, 5, 1, 7 minus lambda. So you knock off the row and column of that. There's your minor matrix right there. And then it'll be plus 0 times a matrix. Actually, this will be plus minus. It will be minus 0 times a matrix. Then it says plus 0 times a matrix. And then minus 0 times a matrix when you do the rest of them. But those guys are 0, so it just kills off. Now, how do you take determinant of us 3 by 3? Well, again, I'm going to expand by the first column. That's your first positive position. So this is 2 minus lambda times this guy, which is 2 minus lambda. And then if you knock off the row and column with this guy on it, you get negative 4 minus lambda, 1, 0, 7 minus lambda. Now you finally got it down to a 2 by 2. How do you take a determinant of a 2 by 2? Main diagonal minus off diagonal. Main diagonal minus off diagonal gives you this. 2 minus lambda times 2 minus lambda times negative 4 minus lambda times 7 minus lambda minus 1 times 0 is 0. But minus 0 goes away, So I get my characteristic equation of 2 minus lambda times 2 minus lambda times negative 4 minus lambda times 7 minus lambda. There, and they set it equal to 0. There is the characteristic equation. Now, from the characteristic equation, can you please tell me what the eigenvalues are? What would my eigenvalues be? Well, it's already factored. Merry Christmas on that one. So you just set each factor equal to 0. So this would be 2 minus lambda equals 0, 2 minus lambda equals 0, negative 4 minus lambda equals 0, and 7 minus lambda equals 0. Solving for lambda, I get lambda equal 2, and I get lambda equal 2 twice, so that has a multiplicity of 2. Solving for lambda, add lambda to both sides, so lambda equals negative 4, add lambda, and lambda equals 7. So I get 2 with multiplicity 2, which means it's an eigenvalue twice. Lambda equals negative 4, and lambda equals 7. But I didn't have to do all this work to do that one. You should have been able to see that one right from the get-go. And that is this. Look at the original matrix A up here. What kind of matrix is it? Triangular. This one happens to be what we call upper triangular. You got the main diagonal right here, and the upper triangular is the non-zero numbers, the lower triangular zeros. So this is upper triangular. And we said, it was a theorem that said that the eigenvalues on a triangular matrix, whether it be upper or lower, doesn't really matter. The eigenvalues on the triangular matrix, on a triangular matrix, is the entries on the diagonal. What's my entries on the diagonal? 2, 2, negative 4, and 7. I got lambda equals 2, multiplicity 2, means it's twice, negative 4 and 7, negative 4 and 7. And then from there, I can work backwards and come up with the factors and then stick all the factors together. Does that make sense? Okay? So, there we go. Now, again, how could I actually mess you up on something like this? If I made this like in a multiple choice kind of a question, you know, if I ask you, what is the characteristic equation in standard form? What would standard form be? It's not the factored form. So what you got here is, you got, 2 minus lambda, put it right here, 2 minus lambda times 2 minus lambda times negative 4 minus lambda times 7 minus lambda equal to 0. I'm going to basically multiply this out, so this would be a FOIL thing here. So 2 times 2 is 4, 2 times minus lambda is negative 2 lambda, negative lambda times 2 is another minus 2 lambda, minus 2 lambda, minus 2 lambda is a minus 4 lambda, and a minus lambda times a minus lambda is a plus a lambda squared. And I would FOIL this part out here, okay? And this would give me negative 4 times 7 is a negative 28. Negative 4 times a negative lambda is a plus 4 lambda. Negative lambda times 7 is a minus 7 lambda. Minus 7 lambda plus 4 lambda is a minus 3 lambda. And a negative lambda plus a negative lambda is a plus a lambda squared. Writing it this way bothers people, so I would rewrite it. Lambda squared minus 4 lambda plus 4 times lambda squared minus 3 lambda minus 28. And then I'm going to FOIL it one more time. You get your standard form of your characteristic equation. Lambda squared times lambda squared is lambda to the 4th. Lambda squared times a negative 3 lambda is a negative 3 lambda cubed. Lambda squared times a minus 28 is minus 28 lambda squared. Negative 4 lambda times a lambda squared is a minus 4 lambda cubed. Negative 4 lambda times a negative 3 lambda is a plus 12 lambda squared. Negative 4 lambda times a negative 28. Big, so grab my calculator here, just make sure I don't screw it up. Negative 4 times a negative 28 is 112 plus 112 lambda. Okay? And then plus 4 times lambda squared is 4 lambda squared. 4 times a minus 3 lambda is a minus 12 lambda. And 4 times a minus 28 is a negative 112. again equal to 0. And then last but not least, on my awesome foiling method here, is I'm going to combine like terms. I got a lambda to the 4th, okay? And I got a minus 3 lambda cubed minus 4 lambda cubed is a negative 7 lambda cubed. And I like to put little lines through them to let me know I've already used those terms. Lambda squared, I got minus 28 plus 12. What's that? Minus 16. Got lambda squared. So let me underline these guys. Minus 16 lambda squared plus 4 lambda squared is a minus 12 lambda squared. So I get a minus 12 lambda squared. 112 lambda minus 12 lambda is pretty much plus a 100 lambda. Minus 112 equals 0. This is what they traditionally constitute a characteristic equation in standard form. Just fancy terminology with this guy. Does that make sense? So, but this one's kind of large here, all right? So what would you do about a problem like this? A 5 by 5 matrix has a characteristic equation of lambda to the 5th minus 4 lambda to the 4th plus 3 lambda cubed equal to 0. How would you find the eigenvalues? Okay? Well, this one again, try not to mess you guys up, it's not too bad. I want to basically solve for lambda here. Well, each term has a lambda in it, and because that lambda cubed, I believe I can factor out a lambda cubed out of these guys, leave me with a lambda squared minus 4 times a lambda plus 3 equals 0. Now this lambda cubed times the lambda squared minus 4 lambda plus 3 is a quadratic, and you hope and pray it factors, otherwise quadratic formula with you guys on this one. So what times what is 3? That adds up to be 4. It's got to be 3 and 1. It's a minus, so they have the same sign. Since the middle terms are, excuse me, it's a plus, they have the same sign. Since the middle terms are minus, they're both going to be minuses. Equal to 0. You set each factor equal to 0. You solve. Lambda cubed equals 0. Take the cube root of both sides. Lambda equals 0. Here, add lambda to both sides. Add 3 to both sides. You get lambda equals 3. And here I got lambda minus 1 equals 0. Add 1. Lambda equals 1. One other aspect of this thing is this. How many eigenvalues did I actually get? Well, officially, 3 of them. 0, 3, and 1, right? But because it's 5 by 5, I'm supposed to have 5 of them. Well, these powers give this multiplicity, which means this couple of the, one of these particular eigenvalues shows up more than once. And which one is it? The 0. And because of that cube there, it has a multiplicity of 3. Because you had to take the cube root of both sides. So this is going to be a 0 3 times, and there's another lambda, and there's another lambda. So grand total, how many eigenvalues do I have? 5 of them. Eigenvalues, there are actually 5 of them, which goes with that 5 by 5. That's what you're looking for. So that multiplicity, you kind of keep that in the back of your mind. That's in this case, for example, lambda equals 0 shows up 3 times with the other 2 eigenvalues. That gives me a grand total of 5, which should always match what the size of the matrix is. Yeah?
So you said that you can get multiplicity 3 because
Because it's cubed, right.
and then when you add the other 2, that's you get 5.
Yes. Yes. So this is, there's 3 of these, there's 1 of them and 1 of them, grand total 5. Right. And it matches up to why we told you about the 5 by 5. And with your characteristic equation, what was the degree of this characteristic, called polynomial, if you will, characteristic equation? it was a degree 5, which tells me I should have 5 zeros. But 0 is a 0, but it's actually there 5 times. So it's an eigenvalue, 3 times. Eigenvalue 3 times, that's what I mean by the multiplicity 3. Yeah.
So if you have a situation where it was like a degree 5, but you got anything other than that, is that not?
Well, yes and no. Degree 5 is going to tell me how many solutions I should have for the polynomial. The one thing that I have not mentioned to you, which we're not going to go into in great detail, but it is a text a section in your book called section 5.5. What if the eigenvalues are complex? If you allow me to have complex eigenvalues, then the degree of the degree of the characteristic equation will always be the number of zeros you're going to, or the eigenvalues you're going to get. But, you know, with complexes, I could literally only have 3 real complexes, and the other 2 are going to be, you know, two real ones and 2 complex ones or something like that. Give me a degree 4, which is what it started out to be, or something like that. So it is possible, to answer your question. Yes, it is possible, but you're going to have to go into the realm of complex eigenvectors and eigenvalues. And then we're going to get into some strange situations on that, which are Jordan canonical forms and the like.
So for us, we're probably just gonna be at the 5 point.
Exactly. We're going to be focused on the real zeros and not the complex zeros. Okay? All right. Again, just reviewing and practicing on what we discussed last time. So, definition. Let A and B be matrices. Definition. A, matrix A, is similar to B if there exists an invertible matrix P such that A is equal to P times B times P inverse. So, similar matrix. Similar, meaning they're not equal. They're not the exact same matrix. But they are close enough that they're going to have certain properties just like each other. That's what we mean by similar. But for a matrix A to be similar to a matrix B, there must exist an invertible matrix, P. So if it's invertible, P's got to be there and P inverse has got to be there, such that when I take A, it will be equal to P times the B times the P inverse. One of your matrix shows up on the left, the other inverse shows up on the right, and then you got your matrix in the middle. If you put that together, you actually get back to where you started from, which was matrix A. And if you notice that if A is similar to B, B is going to be similar to A in the same fashion, what gets rid of P matrix? B gets invertible, it's P inverse. If you multiply P inverse on both sides, you get P inverse on the left of A. What gets rid of a P inverse is you multiply by P on the right. So if A is equal to P, B, P inverse, then B is going to be equal to P inverse A, P on the left. And which is, well, it doesn't matter who's the inverse and who's not. If A is similar to B, B is going to be similar to A. So you can go both ways as you look at the definition. All right. Why do we care? Big theorem. If A and B are n by n similar matrices, then they have the same characteristic equation, which also implies they have the same eigenvalues. Similar matrices have the same characteristic equation, hence have the same eigenvalues. Okay? Let's prove this guy. All right, so here we go. Give A and B are similar matrices. By definition, there exists an invertible matrix P such that A is equal to P, B, P inverse. That's what we mean when we say it is symmetrical. Similar. A is equal to P, B, P inverse. There exists this guy, P, square matrix, says he's invertible. So A is equal to P, B, P inverse. Okay? The characteristic equation of matrix A is the determinant of A minus A minus lambda I equals 0. That is my definition of what a characteristic equation is of a particular matrix. You take the matrix minus lambda I, and you set it equal to 0. Determinant of A minus lambda I. Okay? But as A is equal to P, B, P inverse, thus the determinant of P, B, P inverse minus lambda I is equal to 0 by substitution. But you know which math I did on this guy. I replaced A with P, B, P inverse. Also, P times P inverse is equal to the identity, right? It's an invertible matrix. You take a matrix, multiply by its inverse, you get the identity. And all these matrices, by the way, are the same size, so they're all n by n, okay? Hence, P times the identity times P inverse is also equal to the identity. What's P times the identity is pretty much P times P inverse is you're back to the identity. Thus, the determinant of P, B, P inverse minus lambda times P, I, P inverse is equal to 0. That's by substitution. All I did was replace the identity back here with P, I, P inverse. All right. Here's the big move. And hopefully you remember this, because now we're talking about determinants. Hence, the determinant of P times B minus lambda I times P inverse is equal to 0. How did I go from here to here? What did I do? Follow the math proof, because this is a great math proof. You never know when you're going to have to duplicate it on a test or something. How did I go from here to here? What did I do? You factored a P out of the front. Now, lambda is a constant. Remember that. Lambda is a constant. P is a matrix, B is a matrix, P inverse is a matrix, identity is a matrix. Lambda is nothing but a constant. Constants stay there. But because it's constant, you can put them inside or outside, part of our properties of constants. The P's are in the front, so you can factor that out. The P inverse is in the back. I can factor that guy out. Okay? Now I got a question for you. What is the determinant of A times B? What is it equal to? It was a property you need to remember with determinants. The determinant of A times B is equal to the determinant of A times the determinant of B. So when you have products, you can take a determinant of a product and then take the determinant of each one, assuming that everybody is the same size and square. Does that make sense? Which is what we got here. Hence, I have this. Thus, the determinant of P times the determinant of B minus lambda I times the determinant of P inverse is equal to 0, because the determinant of a product is the product of the determinants. And as, what is the determinant of P inverse equal to? this is a formula you need to know about inverses, so coming back to Hunch and all that inverse stuff. What is the determinant of P inverse, also known as? 1 over the determinant of P. Hence, the determinant of P times the determinant of V minus lambda I times 1 over the determinant of P is equal to 0. And because now these are numbers, the determinant of P and times 1 over the determinant of P are going to cancel, implying that the determinant of B minus lambda I is equal to 0. Thus, the determinant of A minus lambda I equals 0 is the same as the determinant of B minus lambda I equals 0. And once you have the exact same characteristic equation, immediately you get the exact same eigenvalues because you're just taking that characteristic equation and setting it equal to 0. So solve for lambda and you're going to get the same guy because they're the exact same equations, you get the exact same lambdas. Does that make sense? Okay? Now I'm going to put something at the bottom down here so I can sneak it in because I got room and don't want to kill another tree here. Note. If A is rho equivalent okay, there we go. Rho equivalent to B, i.e. A or REF to B, being that's rho equivalent to B, then there exists an invertible matrix and invertible matrix E such that A is equal to E times B. Okay? However, eigenvalues of A and B are usually different, meaning A and B are not similar. All right. Now, I want you to be familiar with this idea of similar. Similar means that there exists this invertible matrix, P, that I could slap one of my matrices by P on the left and P inverse on the right, and I get the other matrix. A is equal to P times B times P inverse. This is not the same thing as, row equivalent or reduced echelon form type thing here. When A is row equivalent to B, so A is REF to B, then there exists an invertible matrix E, E, such that A is equal to EB. Okay? There's no E inverse on the other side. A is equal to EB. And if I have that case, well, okay, great. I can go from A and get row equivalent to B, and there's a matrix that's going to map me down to the row equivalence form of this guy. But that does not mean that these guys are going to have the same eigenvalues. That means if they don't have the same eigenvalues, that means they're not going to have the same characteristic equation. And if they don't have the same characteristic equation, then by theorem here, they're not going to be similar. A is a row equivalent to B does not mean that A is similar to B. That's what this basically is telling you. Well, equivalence is not the same thing as similar. Similar is much, much more direct, okay? So, and note, A is equivalent to B is not the same thing as equivalence, okay? It's not the same thing as similar. All right. Let me give you the gist of what's going on in section 5.3. Why do we care? What can we do with this stuff? Now, I've already mentioned a few things with you guys, and which kind of leads me into what I was doing, well, basically what section 5.4 was about. So I've already kind of mentioned it, but I haven't really gone that detailed in it. Why do we care about eigenvectors and eigenvalues? What is so darn special about these guys? Number one, here's the deal. All right, on an eigenvector and eigenvalue, the matrix A multiplied times eigenvector V1 will be the same thing as the constant lambda being multiplied times the eigenvector V1. The eigenvalue times the eigenvector is the same thing as the matrix times the eigenvalue. So in other words, eigenvectors are the places where matrices actually acts like constant multiplication. It's a very special area here. And these guys basically are nice because it's kind of like your combination when you're sitting there trying to figure out and kind of scramble some stuff over. But once I hit the old basis of having an eigenspace, which is your eigenvectors and with the associated eigenvalues, the matrix acts like a constant multiplication. So in that world, the math is real easy to do versus the convoluted matrix multiplication stuff. Now, another aspect of actually having eigenvectors and eigenvalues is something called being able to diagonalize a particular matrix. Now listen up. All matrices may not be diagonalizable. Okay? These guys are still kind of special here, but let me explain why. This is what we want. What's a diagonal matrix? D is a diagonal matrix means you get entries on the main diagonal and zeros above and below. So yes, a diagonal matrix is triangular, but it's triangular upper and triangular lower at the same time. Zeros above and below, so the only non-zero entries are going to actually show up on the diagonal. Does that make sense? That's called a diagonal matrix. So, we want to figure out this. A particular matrix A. Is there a diagonal matrix D where A is similar to matrix D? Where D is similar to matrix A, if possible. A is equal to some P times D times P inverse. So these two guys have the same format. There's this invertible matrix P where I can multiply P times the diagonal matrix times P inverse, and I'll get that A matrix back again. A is similar to a very special diagonal matrix. This is what we want. Why? Okay. So I got a question for you. If I let D equal to something small, the matrix -2, 0, 0, 5. And I called him D for a reason. He's a diagonal matrix. 2 by 2, granted. -2, 0, 0, 5. Then could you guys tell me what is D squared equal to? D squared. Well, D squared would be D times D. I'll help you out with that. That would be -2, 0, 0, 5 times -2, 0, 0, 5. Row by column. First row, first column, -2 times -2 would be -2 squared. Plus 0 times 0 is 0. Okay. Second row, first column, -2 times 0 is 0. 0 times 5 is 0. Second row, first column, 0 times -2 is 0. 5 times 0 is 0. 0 plus 0 is 0. And then last row, second row, second column. 0 times 0 is 0. 5 times 5 is 5 squared. Granted, it's 25, but I'm writing it like this for a reason. What happens when I square a diagonal matrix? That square on the outside only affects the entries on the diagonal. It's -2 squared and 5 squared. Yeah, you got the answer. The answer is what? 40025. Granted, look at this guy right here. It's the diagonals just being squared. That's the only effect. It doesn't affect the zeros on the off diagonal. Okay? So, if you understand that, please tell me what is d cubed going to be equal to? Cube would be -2 cubed, 0, 0, and 5 cubed, which would be -2 cubed is -8, 0, 0, 5 cubed is 125. So what we're telling you guys is this. If you're going to start doing powers of matrices, you know, cube, squared, to the n power, or whatever the case may be, if you've got a diagonal matrix, it makes it real simple to power stuff up. All you got to do is power the entries on the diagonal. However, if it is not a diagonal matrix, well, then you don't have a choice. You're going to have to multiply b times b times b times b. You like to have diagonal matrices because of this. ... What would b d to the k be equal to? What would that look like in terms of a matrix with d times d times d times d, k times? That's going to be -2 to the k, 0, 0, and 5 to the k. That is what d to the k is going to end up being. Does that make sense? Now, from a computer science perspective, here's the deal. I mean, if I got a diagonal matrix, yeah, it's sweet. I can power up that sucker by just powering up the diagonals. But that's not what I got. What I got here is this. Right down here. Therefore, a to the k, what would that be equal to? Well, if A is similar to a diagonal matrix, P, D, P inverse. If you got A is similar to D, right? A is equal to P, D, P inverse. Well, what would A to the K be? A to the K would be the same thing as P, D, P inverse to the K. Got your pattern here. Which would be, well, I got K copies of this P, D, P inverse. Let's see here. This would be PDP inverse times PDP inverse times PDP inverse, ... times PD. And how many of these guys do I have? K of them. Does that make sense? Clean it up. What happens? The P inverse times the P, when you get rid of the parentheses, is going to cancel. The P inverse times the P is going to cancel. The P inverse times the P eventually is going to cancel. What you're going to be left with is you're going to have that P on the outside. You're going to have how many copies of D, because all these P and B inverses cancel. 1, 2, 3, ... K. That'll be D to the K times that outside is going to be, there's one extra P inverse that never got canceled. What does this mean for you guys that are computer science majors? If I want to take K, and I'm going to take matrix A, and powering them up to a K power, 105. Matrix A times matrix A times matrix A, 105 times. I'm going to completely kill some, electricity, and basically the power grid's going to go down because I'm wasting all that energy on multiplying A times A times A. You understand? A is a big old matrix. And I'm going to have 105 copies of him being multiplied, row by column, adding them up, row by column. It gets going to go old quick. But if A is similar to a diagonal matrix, this would be the same thing as P times D to the K times P inverse. And that right there is going to be simple because you just take that K power and just hit it times each entry on the diagonal, raise each entry on the diagonal to the K power. That's simple. That's just basic arithmetic there. Multiply by P and P inverse, so that's 3 multiplications that I have to do instead of K multiplications. Quote, it is easier to power a matrix. That's the big gist right there. It is easier to power up a matrix. Now, you guys are supposed to be into algorithms and stuff like that, and there's lots of algorithms out there. Why is one algorithm better than another algorithm? What's the point of an algorithm? Well, to get a particular procedure done on a particular circumstance. But why would you rank one above another? CPU time. How much time does it take to run one algorithm over the other algorithm? So I could sit there and take matrix A and multiply it out 105 times and come back in 20 minutes and see how the computer's doing on it. Or I could do it this way, take what K A is similar to that diagonal matrix, power up, basically this is just integers here, put that K on the powers on the main diagonal, then multiply it by P and P inverse. So that's 3 multiplication maneuvers I got versus K multiplication maneuvers I got. So it actually saves a lot of time. So again, from a computer science perspective, this is a better algorithm to, quote, power up particular matrices and stuff. Okay? So, more definitions. Definition. A matrix A, n by n, is diagonalizable. Yeah, fancy word to throw at you guys. Diagonalizable. If we can find a P and a D matrix where P is invertible and D is diagonal is a diagonal matrix such that A is equal to P, D, P inverse. So, yes, A is similar to a diagonal matrix. That's a lot of words. So instead of saying A is similar to a diagonal matrix, we could just say A is diagonalizable. If A is diagonalizable, that means there's going to exist a P, square matrix, that's invertible, such that A is equal to P, D, P inverse. We call that A is a diagonalizable matrix. Just, again, terminology here. Theorem. If an n by n matrix A, which means I'm telling you A's got to be square, is diagonalizable if and only if A has, here it is, n linearly independent eigenvectors. So here's one way to figure out if you're going to have a particular diagonalizable matrix. And that is similar, A being similar to a diagonalizable matrix. You look at the eigenvectors, and if the eigenvectors are linearly independent, and they're n of them, n being, remember, A is n by n, so that kind of matches up here. You've got to have n linearly independent eigenvectors. You don't always get that, but if you do, then A is going to be diagonalizable. If you don't have that, A will not be diagonalizable. Certain matrices will not be diagonalizable, okay? I won't be able to be similar to a diagonal matrix. All right, so, theorem. If an n by n matrix A is diagonalizable if and only if A has n linearly independent eigenvectors, and if A has eigenvalues of lambda 1, lambda 2, lambda n, and corresponding eigenvectors v1, v2 out to vn, which are linearly independent, then here's the big deal. What does your D matrix going to look like? D matrix is going to be a diagonal matrix, and the actual entries on the diagonal are the eigenvalues. Lambda 1, lambda 2, lambda 3, lambda n. So you get the eigenvalues on the diagonal matrix, on the main diagonal of the diagonal matrix here. And better than that, look at what P turns into. You take the eigenvectors and they match up here. This is key. So lambda 1 has eigenvector V1. Lambda 2 has eigenvector V2. Lambda n has eigenvector Vn. You put them in a column matrix, and that's how you create the P matrix. So finding this diagonal matrix and finding the P matrix is simple. You take the eigenvalues, they show up on that main diagonal of the diagonalizable matrix there, and on the diagonal matrix, and the P matrix is actually the columns of the eigenvectors. And because they're linearly independent, that also means you can find the inverse of that matrix. So you get P and you get P inverse pretty much for free, because if they're linearly independent, that's why we have to have linearly independent. If B1, B2, if these guys are not linearly independent, then the inverse doesn't exist. And then you, again, it completely collapses. You won't have a diagonal. A will not be similar to a diagonal matrix. A will not be diagonalizable. So, getting the pattern down and how it all ties together, we got to do a problem. So, I've got to start you out small. By 2. Let A be equal to 2, 3, 4, 1. Find D and P such that A is diagonalizable if possible. And I'll put that word if possible, and I'll put that on the test because it may not be possible. What makes it possible to be diagonalizable? You got to have linearly independent eigenvectors. Okay? So here we go. First thing I'm going to do here is I'm going to find, if you want steps, I'll give you steps. I'll put it in number 1 here. Let's go for the characteristic equation. Characteristic equation for matrix A. This will be the determinant of A minus lambda I. This would be the determinant of 2 minus lambda, 3, 4, 1 minus lambda. I basically just take the main diagonal and subtract off lambda. And again, of course, for the characteristic equation, you got to set it equal to 0. So let's do this. How do you take a determinant of a 2 by 2? Main diagonal minus off diagonal. So this would be equal to 2 minus lambda times 1 minus lambda minus 3 times 4. Main diagonal minus off diagonal. Again, will be equal to 0. I'm going to have to clean this up, so I'm going to FOIL this part out. 2 times 1 is 2. 2 times minus lambda is minus 2 lambda. Minus 1 times minus lambda times 1 is minus 1 lambda. And then minus lambda times a minus lambda is a plus lambda squared. And then minus 3 times 4 is 12. Equals 0. I like to put my characteristic equation in standard form, decreasing polynomial form there. So this would be lambda squared minus 2 lambda minus lambda would be a minus 3 lambda. 2 minus 12 is minus 10 equals 0. This right here is your characteristic equation for A. Take it all the way. Once you get you got to find the eigenvalues, then you got to find the eigenvectors. Now watch what happens and write this down to remind you of what to expect. All right, so you got this quadratic equation equal to 0. Well, you hope and pray it factors, which on my test it will. Lambda, lambda. What times what is 10 that differ by 3? 2 and 5. And because it's a minus, they have opposite signs. Since the middle term's a negative, then the bigger number gets negative, the smaller number gets the plus. So this factors into lambda plus 2 times lambda minus 5. Don't screw this up. It's shameful. This is basic junior high school math. Now, set each factor equal to 0. Lambda plus 2 equals 0. Lambda minus 5 equals 0. Lambda equals negative 2. And lambda equals 5. So we now have the eigenvalues. Now I need the eigenvectors. How do I get the eigenvectors? Let me show you. You take this guy, lambda equals -2, and you go back and plug him into the matrix A minus lambda I. A minus lambda I as a matrix was 2 minus lambda, 3, 4, and 1 minus lambda. It's this matrix here. And then you got the other one, which is lambda equals 5. And you're going to plug it into A minus lambda I, this matrix here. 2 minus lambda, 3, 4, 1 minus lambda. Now, plug in lambda is equal to -2. I end up getting, what is 2 minus -2? Now, I'll try again. 2 minus -2. 4. 3, 4, and what's 1 minus -2? 3. Okay? Now, you get a matrix. You want to solve for this V1, V2, where the thing's going to be equal to 0. This, when you solve for V1, V2, this is going to be your eigenvector. But to solve in a matrix equal to 0, you get this. Basically augment 4, 3, 4, 3, augment with 0, 0. And then you're going to do reduced row echelon form. And notice what you get immediately. And this will happen to you every time. You got to get at least one row of zeros. What is negative row 1 plus row 2? Well, they're the same. Row 1 and row 2 are the same. So when you subtract one from the other, you're going to get a row of zeros. And make it reduced row echelon form. This will be a pivot. That'll be 1. This will be 3/4. Augment 0, 0, 0, 0. That's what you get, and you should be able to see that in your head, because this row 1 is equal to row 2, so it's easily eliminated. You got a row of zeros. And then make the first guy a pivot by multiplying by, in this case, 1/4. But now how do I get this? Rewrite this guy back as an equation. This is V1 and V2. So V1 plus 3/4 V2 is equal to 0. So V1 would be negative 3/4 V2. And then you write it as a parametric equation. V1 is equal to negative 3/4 V2. V2 is equal to V2 because it's free. Okay, so it's a free variable here. And so when you factor it out, I get V1 and V2 is equal to negative 3/4 1 times V2. Now, you know, what you want is this ratio right here. And you could have basically just pulled out a V2 over 4 and make this negative 3/1 if you want to, or negative 3/4 if you want to. If you like whole numbers, great. I don't care. I just pull out the V2 and I get myself an eigenvalue. It's the ratio of the two guys together. So, for lambda equals -2, I got the eigenvector of negative 3/4 1. Now let's find the same thing for lambda equals 5. So with lambda equals 5, when I plug it in, let's see, A minus 5 times I would give me 2 minus 5 is negative 3, 3, 4, and 4 minus 5 is negative 4. Okay? So I'm going to take this guy, negative 3, 3, 4, negative 4, multiply by another V1, V2, set it equal to the 0 vector, and I'm going to solve for this guy. Okay? So this would be the same thing as negative 3, 3, 4, negative 4, augment with 0, 0. And then I'm going to reduce row echelon form this guy. I'm going to make this guy a pivot, so it'll be 1. This would be negative 1, augment 0, with the 4, negative 4, 0. And when I do my row reduction here, multiply first equation by negative 4, add it to the second equation, you'll end up getting a, what a surprise, row of zeros. 1, negative 1, 0, 0, augment with 0, 0. Remember, this represents V1 and V2 here. So I end up getting the equation V1 minus V2 equals 0, which means V1 equals V2. So if I write as an equation V1 and V2, V1 is equal to negative V, I see, add both sides, positive V2. V2 equals V2 because it's free. Factor out the V2, you get 1, 1 times V2, and therefore you get the eigenvector, in this case, 1, 1. Get your eigenvectors and eigenvalues. Why do you care? Bum, 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 bum. Here it comes. Remember, A was equal to 2, 3, 4, 1. With lambda is equal to negative 2, I got the eigenvector of negative 3/4, 1. With lambda equals 5, I get the eigenvector of 1, 1. So, who is A similar to? A is equal to PD P inverse, where D is equal to, and this is your choice. You want to put your eigenvalues on the main diagonal. I like to put them in order, so I'm going to put negative 2 here and 5 here, 0, 0. That is your diagonal matrix. So who would P be equal to? You see negative 2 is in the first column. You see that? So you're going to put its eigenvector, negative 3/4, 1, in the first column. And then 5, the eigenvalue is in the second column. So I'm going to put in the second column the eigenvector 1, 1. And then you've got your P and your D. You can find P inverse by finding the inverse of this guy. And then you got your similar matrix stuff in here. That's how the game is played. Eigenvectors. Now look, here's also the deal. If some of you people are going to put them out of order because you can't help yourselves, and you write it as 5, 0, 0, negative 2, that does change what P is going to be. Since you put the 5 in the first column, you've got to put its eigenvector 1, 1 in the first column. And since negative 2 eigenvalue is in the second column, the negative 3/4, 1 has got to be in the second column. This would be the P matrix. So order matters is what I'm trying to get at. Does that make sense? And now you can actually go and power up this guy. It'll be the same thing as powering up this guy, and that's just P times the powering up of D, which is multiplied by the diagonal, and then P inverse. Okay? We'll do another one next time when we get back. So don't forget, enjoy your Thanksgiving. We got your homework number 3 will be due when we come back on that Thursday, and the test will be on December the 1st, and I'll post all this stuff on Canvas. So see you guys later.